So here we're going to talk about the usage of magnetism in MRI and X-ray imaging. Let's give an introduction in the beginning. The magnetism and X-ray imaging are two interconnected areas of physics that play essential roles in both science and medicine. Magnetism deals with the forces produced by moving charges, while X-ray imaging uses high-energy electromagnetic radiation to visualize the structures inside the body. In this presentation, we're going to explore how magnetic field and X-rays work together in technologies like MRI. So the basics of magnetism. The magnetism arises from moving electric charges. Every electron creates a tiny magnetic field due to its spin and motion around the nucleus. When these fields align, the materials become magnetic. There are three types of magnetic, which are ferromagnetic, the paramagnetic, and diamagnetic. The magnetic fields are visualized by the field lines that emerge from the North Pole and enter the South Pole. Fields and forces. A magnetic field exerts a force on a moving charge or a current carrying wire. The force is given by F equals to the charge times the velocity times the magnetic field times the sine theta. Or if you want to measure it in a current carrying wire, it got to be the force equals to the current times the length of the wire times the magnetic field and the sine theta. The right hand rule, which we learned it in our class, helps us to determine the direction of the field and the force. This concept is essential in understanding how electric currents produce a motion in devices like motors. So now let's talk about the X-rays. X-rays are a form of electromagnetic radiation with a very short wavelength and a high energy. They are produced when fast-moving electrons strike a metal target, usually a tungsten. Because of their high energy, the X-rays can penetrate most materials and reveal internal structures. This property makes them extremely useful in medical imaging and material testing. How X-ray works. In an X-ray machine, the electrons are accelerated by a high voltage and collide with a metal anode. So what's the anode? The anode is a tungsten target inside the X-ray tube where the high-speed electrons hit and produce X-rays. These rays would pass through the body, and denser materials like bone would absorb more X-rays, appearing white on the image. But the soft tissues would absorb less and appear darker, creating a detailed contrast image used by doctors for diagnosis. The magnetism in MRI. The magnetic resonance imaging, which we call it MRI, uses a strong magnetic field and radio waves to create detailed images of organs and tissues. When a patient is placed inside the MRI scanner, the magnetic field causes hydrogen nuclei in the body to align with the field. A short pulse of radio waves then knocks these nuclei out of the alignment. When the pulse stops, the nuclei return to their original position and release small amounts of electromagnetic energy. The MRI sensors detect these signals and a computer converts them into images. Unlike the X-rays, which use ionizing radiation, the MRI depends only on the magnetic field and electric interaction. An application of electromagnetism that shows how changing magnetic field can produce measurable electric signals. Alright, so after these informations, let's compare these two. The X-rays provide a quick imaging of dense structures like bones, while MRI offers a detailed image of soft tissues such as the brain and muscles. The X-rays use ionizing radiation, which carries some risks with repeated exposure, while MRI uses the magnetic field, which are safer for most patients. Each technology serves unique diagnosis purposes depending on the medical needs. The physics behind these two. Both magnetism and X-rays are unified under the laws of electromagnetism, described by Maxwell's equation, especially the Faraday's law, which we learned in class. These equations connect the electric field and the magnetic field, showing that changing the electric field would produce a magnetic field and vice versa. In an X-ray tube, this principle appears when accelerated electrons strike a metal target, releasing their kinetic energy as electromagnetic radiation, which are X-rays. In MRI, the oscillating magnetic fields and radio waves interact with the hydrogen nuclei in the body, causing them to emit detectable electromagnetic signals. Together, these technologies demonstrate how the same physical laws can create very different tools. One for structural imaging through the radiation, and the other for soft tissue imaging through the magnetic resonance. Maxwell equations. The Faraday's law says changing the magnetic field would create an electric field. Why it matters for X-rays? Well, the X-rays are electromagnetic waves, and all the electromagnetic waves exist because electric and magnetic field keep creating each other as they change. The magnetic part of the X-ray wave is produced by changing electric field. And if we give electric current to those changing electric fields, would create a magnetic field. The accelerating electric charges, like electrons, would create a changing magnetic field. And those changing fields help us to produce the electromagnetic radiation, which are the X-rays. Beyond the hospitals, the X-rays are used in airport security, astronomy, and etc. Magnetic fields are essential in motors, generators, and data storage. Together, these phenomena showcase the power of electromagnetism in shaping the modern technology and medicine.